I'm going to talk today about activities that are underway in the United States, but also in Europe and elsewhere to develop a new kind of electricity utility grid called a smart grid. And I'm going to try to make a case for why buildings are a key part of that process. Some of the examples that I'll talk about and the information that I'll give during my talk are U.S.-centric. That's because that's the place I live and the things that I know best, but I think that they're broadly applicable in the UK and Europe and in other parts of the world. If we take a look at the current electric grid, I think we can all agree that it's a pretty amazing achievement. In fact, the National Academy of Engineering had declared that it's the supreme engineering achievement of the 20th century. And when you consider all the ways in which electricity has changed our lives and our cultures, I think it's pretty wide. If you take a look at what's happening with our grid today, though, you would find, if Thomas Edison were to come back, he probably wouldn't find much difference from when it first began. These photos are some old photos of New York around the beginnings of the electric era. And if you look at the structure that we have today, it's very much like what was created and put in place at that time. And in effect, this slide shows sort of the progress of what we have now. So we have markets and operations that take care of business aspects of the electricity grid. We have large central generation facilities that are linked to high voltage long distance transmission lines that go to a local distribution system, and then we have feeders to individual homes and loads. So it's characterized by very much a one-way flow of electricity with very much centralized control of the generation. And another characteristic of it is there's very little information about what's happening as the electrons pass through this system. In many cases, there's very little feedback to the controls and operation centers about what's going on. And so that's the typical situation that we have today. I want to give you some sort of scale of the size and importance of the electric grid. These numbers are, of course, from the United States. But in the U.S., there are over 3,000 electric utility companies, over 10,000 power generating plants, 157,000 miles of high voltage distribution lines that spread that electricity throughout the country, 140 million meters, 800 billion in assets of various kinds that make up the system, and the revenues from the sale and production and sale of the electricity is over $247 billion a year. So by all these measures, it's a truly large system, and that's part of the complexity in making the change. This graph shows a daily load cycle from a regional transmission operator that serves an area in the mid-Atlantic part of the United States, about 13 states in the District of Columbia. And this is sort of a typical one-hour day cycle. What you see is a plot of the normalized electric load on the y-axis and time of day on the x-axis. And it has a characteristic shape where there's a very low demand during the night, and then it builds up to a fairly broad peak in the early afternoon and then tapers off. And this slide also shows the sources of electricity generation that make up this component. So we have base load generators that are largely nuclear and hydro plants, and in some cases there's some renewable as well. We have power plants that are so-called load following plants that are moderated to try to meet change in load during the day, and then we have specialty peaking plants that come online for meeting the short-term peak needs. And there are different costs and environmental constraints for each one of these kinds of plants, and so that's one of the issues that we face in looking at how to modernize our system. Let me pause here. I see a note from Richard. Okay. Another way to look at that information is to plot it in a different way. What you see here is load on the y-axis again, and the percent of hours that we have that much load. And what you can see by looking at this curve is that there's a very sharp uprise at the end. And this data shows that for this region of the United States, about 20% of the generating capacity is only used about 5% of the time. So one of our challenges is to try to figure out how to make a better use of these generating resources so that they're more broadly used throughout the day, and we get rid of some of this peaking problem that so dominates the consumption of electricity. Another issue that's coming to the fore is what happens as we migrate towards an economy where we have broad use of electric vehicles. We have policies in the United States to try to encourage the growth and use of electric vehicles. There are plans to put 1.6 million vehicles on the road in the next few years. And there was a study done in California to take a look at what impact that might have on the electricity grid. And what you see at the bottom of this slide are two graphs showing different scenarios for how charging of electric vehicles are managed. On the left-hand side, you see a case where there's no particular constraints that are placed at all, and it's sort of a prediction of what people will do absent any other incentives. And it looks very much like you would predict. People will go about their day, and then when they return home in the afternoon from their work or whatever their other activities are, they'll plug in their car, and their cars will begin to charge. And so the net effect is a sharp increase in the peak, and also a long tail driving off until later in the day. What you see on the right-hand plot is what might happen if we can have the appropriate incentives and smart charging kind of capabilities so that cars would delay charging and try to make use of low demand times during the evening, and you might be able to sort of fill in some of this evening trough and reduce the increase in peak. So one of our goals of Smart Grid is to try to figure out how to deal with those sorts of issues. Another challenge for Smart Grid is ways in which we might increase the use of renewable energy sources. What you see in this plot is an example of the load in megawatts versus time of day, much like before. So this red curve is the familiar shape that we've seen in the other graphs. Superimposed on that in this blue line is some information about the generating capacity that this utility has from wind power. Now, note that the scales are different. The scale of the wind power axis is on the right and the total load is on the left. So the magnitudes are quite different. But there are two very interesting facets to this that are important. One is that you can note that a lot of the availability of wind, in fact, the dominant availability in this region of the country, is during the hours when we don't need extra generating capacity. So we have a mismatch in time of day between the availability of this renewable resource and the demand. The other thing that you can see from this blue line is that there's a lot of variation in the generation capacity, and that reflects the changes in wind speed. So we have two problems when we look at integrating large amounts of renewable energy. One is being sure that the energy source matches the time of day when we want to use the energy, and the other is trying to find some way to manage these fluctuations that take place. So if we take a look at what the vision is for Smart Grid and the goals for the whole overall activity, we see several key points. One is that we would like to be able to engage customers or the people who consume the electricity to do two things. One is to improve their energy efficiency by reducing the total amount of energy consumed. We would also like to be able to reduce the peak energy so we can have more uniform use of our distribution and generation sources. We would also like to be able to increase the use of renewable resources, so we need ways to deal with these two problems that I just mentioned. There are also issues with reliability and security. Today, when there are failures in the electric grid due to storms or other kinds of occurrences, it can be difficult to track down where they are exactly, and it can be difficult to, in a short time, reroute electricity to avoid having severe, widespread outages. And part of the idea behind the new Smart Grid will be to improve the kind of data collection and response capability for those sort of events. And finally, we would like the grid to be able to facilitate an infrastructure that makes sense to encourage the use of electric vehicles. So if we look into a crystal ball and try to figure out what this Smart Grid might look like, here are a list of characteristics that many people think we might see. First is we would see an increased use in renewable energy. There are some predictions in areas of the U.S. this might be as high as 35% by 2020. We think we'll see a change from this monolithic one-way grid to something called microgrids. In other words, we would have a much more distributed generation capacity and many generators that are much smaller scale than the kind of large plants that we have now, so we could have more autonomy and interactions between these smaller grids. There will be a need for bidirectional metering and bidirectional information. So if your buildings are generators of power, you might at one time be putting power back into the grid, selling it, if you will, to the utility. And at other times you might be consuming power from the grid. We're already beginning to see that happen in many places, particularly with photovoltaics. These changes in the generating capacity of renewable energies cry out for storage techniques that might be used. And it's quite likely those will need to be distributed so that we can have storage closer to the use. So there'll be a need for that. There'll be a need for smart meters that allow us to make better decisions as we manage facilities based on real-time data. And linked to that are the sort of pricing tariffs that are used to bill people for electricity. Today in the U.S., most consumers just pay a flat rate. In residences, in commercial buildings, they tend to be a bit more complex. But there's an opportunity to use pricing as a way to modify behavior to meet some of the needs that we have for the grid. We also believe that there's going to be emerging very rapidly a whole new generation of home appliances and other kinds of products that have the ability either to communicate directly with signals from the energy provider or else to work through some sort of energy manager in the home or facility to do that so they can collaborate with information that comes from the grid. And I talked a bit before about the plug-in vehicles, and we think that there's going to be a much more sensor-rich environment throughout the grid and throughout the buildings and other places where you consume electricity, so we'll have much more information in order to base our operation decisions on. So in a nutshell, if we take a look at this vision of a smart grid, we're going to continue to see the distribution systems that we have seen in the past, but we're going to overlay on top of that very much an intelligence infrastructure of measurement and communication. Think of it as sort of marrying IT networks to the various hardware and things that go onto the grid today, and also to combine that with renewable energy generation and some local microgrids in addition to the large infrastructure. So very much about what's happening to create a smart grid is about trying to figure out how to describe this information flow and how to make sure that that gets to the right place so we can make better operating decisions. So an obvious question is, what does it have to do with buildings? And I will assert to you that it's impossible to have a smart grid unless we have smart buildings. And the reason for that is because that's where electricity gets consumed. In the United States, 72% of all electricity consumption is in either commercial or residential buildings. If you add to that electricity consumed in industrial buildings and facilities, it goes well over 90%. So virtually all electricity is consumed inside a building of one kind or another. Secondly, there are national goals to try to drive towards more energy efficient operation of buildings, even net zero energy buildings. In order to achieve that, or even come close to achieving that goal, there's going to be increased use of renewable energy which is affiliated with these buildings, whether that be photovoltaics attached to the roof of the building or over parking lots or small-scale wind generation or whatever it might be. Buildings will become a generator of energy as well as a consumer. And finally, as we migrate towards electric vehicles, where are we going to plug them in? They'll be plugged in at your home. They'll be plugged in potentially at your place of work or at a shopping center. But all these charging facilities will be in some way connected with a building. So all these things really point to the fact that if we're going to do anything about combining matching loads to the availability of energy resources, we have to have smart buildings to be able to manage this. Building will no longer be just a dumb load at the end of a wire. It will become an integral part of the smart grid, a partner with the utility and energy providers. So in the United States, in order to try to make this happen, there was a public law that was passed called the Energy Independence and Security Act. And as part of that law, responsibility was assigned to the National Institute of Standards and Technology, NIST, which is where I work, to create a framework, a standards framework to enable this transformation of the technology. And there's a small quote here from the text of that law, that NIST is to coordinate a development of a framework that includes protocols, model standards for information management to achieve interoperability of smart grid devices and systems. So we've been working very hard to carry out this mandate, and it's turned into a fairly large undertaking. This slide shows sort of the overall strategy that's being used to try to make this happen. The first phase began in 2009, and it was really an opportunity to identify what might already exist in the standards world that would be important building blocks for this future smart grid, and to identify where there were gaps and places that needed a lot of work so that we could achieve this goal. And there was a report published in September of 2009 that captured those findings. There's been a revision since that time that was just out for public review and will be published probably in another month or so, which updates the analysis of both what standards are moving along since the initial analysis, and also to fill in some of the details of ways in which the gaps are to be filled. So phase 2 began at the end of that original report, and it involved the creation of something called a smart grid interoperability panel. You can think of this as a committee consisting of a variety of interest groups. There are 22 or 23 different interest categories that have been identified that have a role to play in the smart grid and an interest in the smart grid. And each of these groups has an opportunity to nominate membership in companies and individuals to this committee that addresses filling the gaps of these framework. And this SGIP, as it's called, has identified 18 different priorities that need to be met, and they created what are called priority action plans to try to carry those out to fill in these gaps. And the whole idea behind this group is to try to advance and speed up the normally very slow standards development process so that it can move quickly. And a while after that began, an effort was begun in a phase 3, which is running concurrently with execution of phase 2, which is to develop a framework for being able to do testing and certification of products that might emerge in response to these standards. It's been widely recognized that having something on a piece of paper is not going to be adequate. There needs to be some way to test and verify that actual products comply with the standards so that they'll work as consumers expect. So here's sort of a summary of where we've gone with this SGIP. First, it's a very large organization. There are over 700 member companies or member organizations. Some of them are professional societies. For example, ASHRAE is a member of this SGIP. It's an open process, and all of the meetings that are held of the SGIP and also the various priority action plans are webcasts. There's opportunities for people to participate electronically, and all the documentation that gets generated from these various groups are posted on the internet through a Twiki site that's maintained by NIST. So there's a very big effort that's being made here to try to make this accessible and as inclusive as possible. Over here in the right-hand corner, you can see some websites where you can go to find more detailed information about the SGIP. I want to take that big perspective and try to narrow down to just one piece of this to give you a flavor for how this is taking part, and talk about what's called Priority Action Plan 17, which is to develop a facility smart grid information model. The idea behind this is to create a way to represent the kind of information that the managers of a facility have to have in order to respond and deal correctly with a smart grid environment. And facility is very broadly defined here. It can mean a single-family residence. It can mean a commercial building. It can mean an institutional or industrial facility. In any of those things and all those things come under the umbrella of a facility by this model. And ASHRAE has combined with the National Electrical Manufacturers Association to develop a U.S. standard that would fulfill this need. What you see on the screen here is the text from the purpose of the standard. So the idea is to describe an abstract information model that would enable appliances, control systems in homes, buildings, and industrial facilities to manage both electrical loads and generation resources in collaboration with this new smart grid. This particular committee has 5 different categories of interest that were defined in order to achieve balance. So we have representatives from commercial, institutional, and industrial producers. So these make products that are used in those environments. Groups, members who are from manufacturers of products that are used in residential and consumer electronic roles. People who make these decisions, be they homeowners, people who manage commercial industrial facilities, utility interests, and then so-called general interest. Overall, there are 44 voting members and 5 non-voting members and a consultant. But that doesn't quite capture the scope of the committee. There are many people who are actively involved in this committee's efforts who are not formally members of the committee, because like the SGIP, the process is open to anyone who wishes to participate. And most, but not all, the meetings of this group has also been held electronically. So what's the solution that this group is trying to come up with? This slide sort of depicts a number of physical things that you might want to represent in a facility as part of this abstract information model. Various loads and devices that are in a building, local generation and storage capabilities that you would want to represent and to communicate with the grid. So the idea is to create a building block, an abstract building blocks that can be combined to represent these kinds of entities in a real facility. And the 4 components of the 4 building blocks of this model are an energy manager, which is depicted by the green squares with an EM, the blue squares with an L, those represent loads. Blue with an M is a meter, and the G stands for generator. So the idea is the information model has these 4 components: a load, a generator, a meter, and an energy manager. And by defining the characteristics of these abstract ideas, we can combine them in ways to represent physical devices. So for example, let's take a meter. If we have a device which is simply a way of measuring the consumption of electricity, that is a meter. But if we have something that is come to be called a smart meter, where it may have some communication and maybe even some control capabilities, those capabilities really are embodied in what we call an energy manager, because you're managing the operation of load. So we would combine these abstract ideas of a meter and an energy manager together to represent that sort of a device. Another example would be storage. Whether it be electrical storage or thermal storage, you can think of a storage device as a generator when you're discharging the storage and as a load when you're charging it. So in order to represent those kinds of things, we combine a load and a generator. We also see a need to be able to aggregate things. When you're trying to manage a facility, you might have some part of your control system which is not looking at one individual load, but a whole collection of loads. So we need to have a way to aggregate them. So a load could be a virtual thing, which is a combination of several real physical loads. Similarly, if you have generation capacity, be it standby emergency generation or renewable generation or something else, maybe hydropower, those things might need to be aggregated. So as you're making facility management decisions, you might need to do it at a level where you're looking at more than one individual device. So the idea is that by defining these abstract building blocks, we can rearrange them in such a way that we can represent all these kinds of devices. Now, the information model is abstract for a reason. We've recognized that when you try to implement this, there are different communication protocols that you're going to run into in different environments. In the commercial building world, you're going to find things like BACnet that are very widely used. In an industrial environment, you're going to find process control technology that's used. In a residential environment, it's a little hard to say what's going to happen because it's largely non-existent at this point, but there are several different contenders. So the consumers of this facility smart grid information model are actually standards groups that will make protocol-specific implementations of this model in order to carry that out using the technology that that group supports. For example, the ASHRAE BACnet committee will be making enhancements to BACnet in order to implement the features and characteristics of this model inside the BACnet protocol. So what capabilities will we be able to implement from this information model? This slide has a list of the kinds of things that are taken into consideration in the various use cases that have been put together by the committee to guide what goes into the model. And it contains things that you would expect to see: on-site generation, demand response, storage systems, management through load shedding of peak demand, the ability to estimate what your future power needs might be so that you can communicate that with the utility to help with planning. Also be able to convey information to your utility provider about what kind of capability you have for shedding loads to help them manage the needs that they have for maintaining the stability of the grid. We'll need to be able to deal with sub-metering so that we can make decisions within our facility about how best to manage our devices. There also may be a need to measure and moderate power quality issues depending on what kind of a facility it is, and include information about what's happened in the past, which could also be helpful for control strategies, and in some cases we think there might even be direct load, as happens in residences today, where the utility might be able to send a signal that turns off or changes the set point for an air conditioner. So we think this model needs to be able to allow all these kinds of actions within a facility. Where do we stand in the development of this? The committee was formed in August of 2010, so it's almost a year and a half old. And we immediately divided into several working groups, and these working groups have been meeting in parallel almost weekly by teleconferences. And we've been having pretty much monthly meetings of the whole project committee. So by standards activities, this is an enormous amount of activity, an enormous number of meetings to try to move this on an expedited fashion. We're nearing having a first public review draft. We have a goal of trying to do that by the end of January. It's not yet clear whether we'll be able to make that goal, but we're pushing very hard to try to do that. So I think we will have some sort of a public review draft that will come soon. We've also already been seeking and reaching out to try to get international participation in this activity. There are a number of places in the international standards world where things are happening related to smart grid. There's already been interest expressed in ISO, in an ISO committee for a home for this product when it comes out, and there's also interest in IEC. And there's a possibility for folks to participate even immediately as soon as we have a public review, because the documents will be available on the internet, and the public review process can all be done electronically, so there's an opportunity for people anywhere in the world to review and comment on this standard as it evolves, even before it's formally submitted for consideration in an international standards body. And I'm just going to end with a couple of places where you can go to look for more information about these things. One is the website we maintain here at NIST that sort of captures at a high level our smart grid activities and the activities that are underway in the U.S., and a place where you can find more detailed information about this particular committee, the ASHRAE NEMA 201P. And with that, I'll stop, and I'll try to work with our host to see if we can find a way to have questions and answers.
Okay, thanks very much, Steve. This is Tim Dwyer from London. We've still got problems with our audio our end, but hopefully you can hear us now.
I can hear you now.
Excellent. That's great. That means everybody can hear us. Alan, could you turn that on? Right. Well, thanks, Stephen, for that. What I'll do, excuse me, I'll pass you across to our chairman, Stephen, Ewan Rose, and he'll just give a few words of welcome, and then after we've done that, we'll pick straight into some questions, if that's okay.
That's fine with me.
Hello, welcome everybody. It's Ewan Rose here. I'm the vice chair of the CIBSE ASHRAE group. I was hoping to welcome you at the beginning of the evening, but it's nice to do it this way around anyway. And I was going to introduce Stephen, but I'll actually thank Stephen for his excellent presentation, which I think we all enjoyed, and I hope everybody heard okay. Apologies for the problems we've been having. We need a smart grid around us to sort out our audio problems, but I think we're getting there now, talking on the phone. I just wanted to say, first of all, which I would have said ahead of Stephen's presentation, is that this event is one of a number of webinars that we are running through the CIBSE ASHRAE group. We're planning to do a lot more next year, hopefully with better audio setup. They've actually been very successful so far, and it's a great way to get a large number of people involved without everybody having to travel. This particular webinar on smart grids is being supported by the Heating and Ventilating Contractors Association, the HVCA, so a big thank you to them. And it's being hosted here at the Centre for Efficient and Renewable Energy in Buildings at London South Bank University. So thank you for their support. Just a few quick words about Stephen Bushby, who you've just been listening to. He works, as he points out, the National Institute for Standards in the U.S., and he was speaking, as you can tell, live from the U.S. He's also chair of ASHRAE's committee developing a model for smart grids. So obviously he's the key man for us through our involvement with ASHRAE. You've heard his presentation. He had a tremendous amount of information. That's a very exciting area. I must admit it's an area for me that I struggle to get my head around because it is just so large. The implications are so great. I think a lot of that came out in Stephen's presentation. I know there's quite a number of you out there online listening to us, and this is your opportunity to get involved. We normally ask people to text in questions. I think a few are coming in. Some we've got here. I mean, one question, Stephen, I assume you can hear me. I'll go and start posing some of these questions. I know there are a lot of, you mentioned there are a lot of bodies involved, a lot of people involved in this, the program that you outlined. And I just wondered how committed you felt the conventional power industry is to this process. I know you have utilities involved, but obviously it's a huge, the greatest implications are for them. I just wondered how committed you felt the utilities, the monolithic people that you referred to are to this process.
I'm not sure if I can answer the question from a worldwide perspective, but I can tell you that in the United States, they're very committed and very much involved. And there are several reasons for that. One is there has been a huge amount of federal government money put into trying to stimulate certain aspects of this. And it was all part of the American Recovery and Renovation Act that was, trying to stimulate our way out of the economic problems that we're in. A large amount of money was provided through the federal government to do things like install infrastructures of smart meters and do other things to help promote the movement of this technology. So there's a lot of money that's been thrown at it, as well as a lot of money. There are also regulatory aspects to this. In the United States, at the state level, there are public utility regulatory commissions that decide issues about price and when utilities can build new generating facilities and so forth. And they're very much involved in this process, and so there's a lot of interest in trying to be sure that what happens here sometimes will take place through these types of regulations. I'm hearing a lot of echo. Can you hear me okay? I'm going to proceed.
Yes, we can hear you. We can hear you fine. Thanks, Stephen. Yes.
Okay. So there's, in some ways, there's a stick that goes with this to try to be sure that utilities do what's in the public interest. And I think there's also a genuine interest in this because the utilities want to play a part in how this gets shaped because they want to be sure that the end result is something that they're very much happy with and can live with in the same way that consumers want that to be the case for them as well. So I think there's a lot of involvement. Where there is a difference sometimes is one of perspective. I think there are a number of people from the utility world that still like to think in terms of the utilities sort of being in complete control of what happens, because historically they have had a sort of a monopolistic role in maintaining the integrity of the electricity grid. And so they're a little nervous about a collaborative arrangement where there are other generation capabilities that they don't control and where there might be large load changes from facilities that they don't have any control over. So some utilities would still very much like for the utility to be in charge. But consumers are very resistant to that, particularly commercial and industrial consumers. As you can well imagine, people who run buildings don't want to have large pieces of equipment switched on and off or their controls made by someone outside the facility because we have no idea what the consequences of that are. So there's a bit of a cultural shift that's taking place that hasn't entirely worked out, but they're very much involved and engaged.
Stephen, thank you. Thank you. That's a very interesting answer. And there's some more questions coming in. I'd just like to pose this other one, though. I mean, this is a very, very important development and interesting what you're talking about. I was just wondering about timescales. I know you're talking about a standard appearing in 2012. What do you, I mean, how much technically needs to be overcome in order to make smart grids a reality? And do you have an idea of when we're going to start seeing the rolling out of smart grids on a commercial scale?
I don't think it's a matter of one day we don't have a smart grid and the next day we do. I think it's a matter of pieces coming along sort of in parallel and developing in ways as we get the technology sorted out and as products begin to appear. So I think we're already seeing early signs of it in terms of what are so-called smart meters that are being installed. And we're beginning to see some new changes in measurement technology that's used by the distribution system. So it's going to come out in bits and pieces. And as far as these standards go, I talked about one particular standard, but we actually think that in the end, there are probably going to be a few hundred standards that are related to smart grid. If you take a look at this NIST framework document, version 1 or version 2 when it comes out in another month or so, you'll see there's already a list of a number of things which have been accepted as critical components of this smart grid standard suite. One that many of you would be familiar with is BACnet. BACnet has been identified as one of those standards. And these priority action plans that were created, some of them are beginning to reach completion. There have already been some standards that have just recently been approved that came through that process. And so I think we're going to see sort of an ongoing chain of these things evolving, and it will start out slowly and then grow over time. So we're beginning to see some implementation now, but I think a radical sort of shift is going to happen over time, and it may be a number of years before you realize how much change has really happened.
Okay, thank you, Stephen. That's great. That's answered that one. We've got a question coming in online from Nick Kimber, and we've also got a question in the room here. So I'm going to go with Nick's question first. Nick's asking, who do you see owning the end device in the house, especially if the consumer has choice over who supplies its electricity? Do you see this being a telco or a utility, there's also communications, I guess, or a utility responsibility, Stephen?
From the standpoint of this facility information model that we're working on, we're trying to accommodate both ideas because we think that the marketplace will be the end decider of how that plays out. My personal view is that there will be some home consumers who decide that they're perfectly happy with just taking a reduction in their electricity rates and letting the utility have control over at least some things in their home. Today it's primarily air conditioners and electric hot water heaters. But my personal view is that as we get more sophisticated and there are more complex interactions with loads in your home, other kinds of appliances, I think people will want to have control over what happens, and I think it will shift to sort of a more price-based kind of thing, where utilities will change prices as they're allowed to by the regulatory authorities to let the prices allow their cost of generation and transmission. And the consumers will pick whether they would like to make changes in their energy consumption patterns in order to reduce costs, or whether they decide they'll pay the extra money and continue to do the things that they wanted to do. So my personal view is that the latter approach, where the consumer has ultimate control and they're going to have price incentives to try to get them to do what you might consider the right thing from a grid standpoint, will probably be prevalent as opposed to utility direct control, but that's just my personal view.
Okay, Stephen, thank you for that. We've got a question here in London in the room, so I'm going to pass over and ask the gentleman to tell us who he is and then pose his question to Stephen.
Hi, Stephen. My name's Jerome Taylor-Lewis, and I work for a company called Kiwi Power in the UK. We are one of the very few demand response aggregators, I'd say very similar to the NNOC model operating in the UK. So I can give a little bit of UK perspective as to how the smart grid works. It is in a commercial sense, it is underway here, and we're basically looking to commercialize the market here. My question to you is the FSGIM, the standard that you're working on. I guess there's a lot of parallels between that and OpenADR that I've been reading about. A lot of work's been going on in that space in the US. So my question is, how do those two standards, how do you see them interlinking? Are they interlinking? Are the two standards working hand in hand to basically have some sort of coordinated approach towards communications to the smart grid?
Okay, that's a great question, Jerome. I'm intrigued by the name of your company, Kiwi Power. My first thought would be New Zealand, a long ways from where you are there in England. But the answer to your question is that this facility information model that we're building is not something that's being created from whole cloth on a clean sheet of paper. We recognize that there's a need to build from things that have already been done. So, for example, the generator component of this model built largely on some work from an IEC standard that relates to, built by the electricity industry for managing their generation resources. It's an IEC 61850, one of the components of that very broad suite of standards. And there's also been some recent standards developed in the United States through OASIS related to what you refer to as OpenADR. There are two of them that are relevant. One of them is called EMIX, which is really an effort to try to characterize how we might define in an electronically exchangeable way what a unit of electricity is, its characteristics in terms of, say, for example, how green it is, and also price information. And closely related to that, something called energy interoperation, which is intended to be a mechanism to allow communication between the energy provider and a consumer, specifically targeted towards things like being able to mitigate peak load, so demand response. And OpenADR is actually a profile or a subset of this energy interoperation standard. Now, how does that fit to our facility model? What we have done is we have taken some of the building blocks from this EMIC standard in particular, which is the pricing information, and we have incorporated those into these four components of our model. So we're trying to reuse those things. So the hope is that what would happen in the real world is that when we make a protocol implementation inside, say, a commercial building, we're going to be doing it in a way that's compatible with what's been done to try to standardize this pricing information and these demand response signals. So what I would imagine happening in an actual building is, let's say it's a BACnet building, and we've got some BACnet system that implements this yet-to-be-born facility smart grid information model. We would probably have a device there which can communicate, presumably over the internet, to an energy provider to exchange these signals for demand response. And it would seamlessly integrate with the control systems and some strategy that's been designed by the facility management of what kind of responses to do for that, so that you can begin taking the appropriate control actions in your facility. So I see a very direct and close coupling, and we're trying to make that easy to do by reusing concepts that are built into some of these other standards. I hope that helps answer your question.
Hello, student. Hello?
Hello, I'm here.
Yeah, hi there. My name's Gordon Lowry, and I'm in the faculty here in the university. I've just got a couple of questions, Stephen, and I'm just interested in really understanding the American perspective on these issues, and they're really concerned with how you sell this to the domestic consumer, the residences. There's 2 points that come to mind. One is that once a smart grid extends into people's homes and you get a good exchange of information, that becomes, in a sense, a form of surveillance. And I wondered whether there's been any, or what consideration has been about protecting personal data in terms of ensuring that the utility company does not get records of when I'm on holiday, when my utilization demonstrates that I'm away for the weekend, the building, my home is empty, and so on. So those kind of security issues. And then an entirely separate point, if I've got an electric vehicle that I'm most likely going to be charging at home, I want to know that it's when I plan to use it, it's going to be fully charged. But if it's going to be used as a energy reservoir, then presumably I can no longer be certain it's fully charged when I want to use it. So I wonder if that's going to be a difficulty as well. So two quite separate points. So
okay, let's start with the security. This SGIP process has a very large committee dealing specifically with cybersecurity issues. And there are sort of two aspects to that. One is, how do you ensure that any information that's being exchanged through communication technology is in fact secure in a couple of senses. One is that people can't see it who don't have access to it, and the other is that there's some kind of proper authentication for individuals who are trying to get access to it or use it in some way. That can include ways in which a consumer might delegate that to an aggregator for certain kinds of activities, which you might agree to do that the aggregator does using all of their clients as opposed to directly between you and the utility. So every one of the standards that comes out of this process has to go through a review by the security committee to be sure that it meets appropriate guidelines. And there are some very extensive publications that have already been put together about what those constraints might be. And I don't have the reference to it at my fingertips, but I could send it to Tim and he could forward it on to folks who are interested. There are some specific documents that have been created for that purpose. So that's one aspect of it. Another aspect of it, which you touched on, is that since we'll have information in a much more fine-grained manner than we have today. Typically today you have usage over some fairly long period, like a month. But with the new measurement and metering technology, there'll be very fine-grained information, and you can detect things like when someone is home and not home and what kind of patterns they have for coming and going. And I don't think we're going to be able to stop measurements at that level of detail. I think the key is going to be, can we keep people from getting access to that data who don't have appropriate authorizations to get it? And so that ties back into the first point of trying to be sure that all the communications are secure, and also the business processes whereby you make arrangements for people to get it are secure. And I think there will probably be federal regulations about what kind of business practices have to be in place to be sure that there are appropriate security measures. So that's, I think, kind of what I can tell you there. Now let's go to the electric vehicle charging. There are people who think that when electric vehicles are available in large number, that they might, in fact, be an opportunity for storage for the grid to deal with short-term peak demands. That's very much an academic idea at this point. I'm not really convinced myself that that's going to be practical on a large scale, given all the inefficiencies of charging and discharging these vehicles and how distributed they are. But there are people who think that that will become very important. And my answer to how the consumer would relate to that would be that there has to be intelligence in these charging stations whereby you can set parameters of what you're willing to do. So if, for example, you think you're going to be making some trips in your vehicle and you'd want to be sure that it doesn't get discharged, you might have a setting that says you're not willing to allow the electricity to be taken out of that battery, even if there is some sort of a request from the energy provider to do that. Whereas at another time, you might be able to set it in a mode whereby you don't think you're going to be using it, so you're perfectly okay with that, and you might get some price breaks for offering that. So I think it will come down to some sort of a selection that the consumer makes about what level of interaction they're willing to allow, and that's the way that you'll control it. That's my view.
Okay, thanks for that, Steve. Gordon, this is Tim Dwyer. Gordon was, I think, reasonably content with your answer there. In actual fact, I had a question I'd just like to ask, and it really just builds on that question of dynamic storage that Gordon was talking about here. I'm absolutely no expert at all in electrical distribution. The only way that I know electricity is stored in the UK is by pumping water up to the top of the hill and letting it go again later in the day when there's electricity is used, using some sort of pumped storage. I don't know if we do anything else in the UK. It may well be other things, but I just wonder, you said, oh well, they will use storage somewhere. It will be distributed, but where? Where's this going to come from? Is Hoover Dam going to be pumped back up or something? What's the idea? Is there any thoughts on this?
I think storage is a really hard nut to crack, and I know that there are a number of research activities underway looking at large-scale storage capabilities. Some of it is in new kinds of liquid battery technologies. Some of it is in mechanical things like flywheel-type storage devices. As you indicated, there are some places where there are efforts to use water to pump it someplace so that you can recover the energy by running it through some sort of a turbine. I think all those things are going to happen, but I think they're all fairly long-term developments. I don't think we have anything which is on the very near-term horizon that's going to make all that viable. I think in the short term, one of the things we're going to have to turn to is changes in the way in which we manage the loads in a building. And this is one of the reasons why I think buildings are a critical part of the smart grid. I think that buildings are themselves potential storage reservoirs. I think we already do some things about, at least in commercial buildings, maybe changing temperature set points for certain periods of time in order to reduce demand. But I think that we may find in all kinds of buildings and manufacturing facilities that we might be able to, at the right price, mitigate loads, even with fairly short-term notices, to help match the load with the available energy. I don't think that's a complete solution. I think in the end we need to have some kind of reliable electricity storage. But I think it's going to be a combination of changing how we operate, changing lighting levels, changing heating and cooling set points, maybe changing some industrial processes to be able to change the way you do the process to mitigate peaks, things of that sort, which will be combined in the long run with energy storage. And I think it's a bit of an open question.
Okay, thanks, Stephen. We're coming quite near the end of our time, but we do have two questions that have just come in from some of our people who are out there on the web. Hassan Yildiz has asked about dynamic demand management. I think you probably just touched a bit on that, dynamic demand management as a technique for leveling out these peaks and troughs in load. Is that right, Stephen? Do you see a big role for that?
Oh, I definitely do. And I don't know about it in the UK, but it's increasingly common in the U.S. to make use of things like ice storage, particularly as a way to store cold, because that's one of the large demands, at least in commercial buildings, is cooling and air conditioning. So today, some of that stuff is staged based on time of prediction of when you think you're going to have hot peaks, but we might be able to make use of those things in short intervals. You might turn off the use of a chiller for a period of 15 or 20 minutes and return to a storage based on some information from the grid, whereas today we wouldn't do that. So I think those kind of things are going to be very important.
Thank you. We've got another question from Daniel Johncock, who's concerned about consumers buying into this. I mean, how much? I noticed in your presentation you did mention consumers involved in some of the groups. He's concerned about whether consumers will accept this concept, whether they think the advantages are all with the power suppliers and not so much with consumers.
I think that's the weakest link. I think that it's a much easier case to address ways in which commercial and institutional and industrial facilities will see a value proposition in this and make changes, because we see some precedent for that already. When you look at the consumer side, there are some significant obstacles. I think there are some classes of consumers for which their utility bill is a real financial strain for them, and they would have a motivation to try to do some of these things. However, those very same folks probably have very limited capital resources to invest in making changes in technology so they could take advantage of it. So for that class of people, there needs to be some way to help deal with those capital costs before they'll be able to be engaged. I think there's a much broader class and much larger class of consumers who don't even pay any attention to their utility bills. They may be a little bit annoyed about it, but it's not a sufficiently high percentage of their daily living costs that they worry about it very much, and I think that's going to be a hard audience to sell. I think some people will move towards this technology simply because they think it's the right thing to do, and maybe they have some enamoration or excitement about the technology, sort of the gee whiz factor. I think that's one part of it, but not everyone will be motivated by that. In the U.S., for some years, we have had federal requirements for energy efficiency of household appliances, things like dishwashers, refrigerators, freezers. You may have that in the U.K., I'm not sure. But I would imagine that there will be some regulations of that sort that mandate certain kinds of capabilities to respond in a smart grid environment that will become required of products that you sell. That'll help make it easier for a consumer to make that choice. But I agree that it's a hard sell to the consumer, and I think that is actually the place where it will last be widely implemented. I think it'll be implemented in commercial and institutional facilities sooner.
Stephen, thank you. So once we have to have the system in place, and then make the hard sell we're really just about out of time. One last question, I think, which would kind of sum up quite nicely, from George Chen online. I'm not sure where George is, but he's coming to us online. George is saying, Stephen, what's the risk to developing the smart grid? Which could probably end our evening on an interesting, nice broad question for you there. What's the risk?
I can tell you that from someone who's sort of in the thick of this, that it's an amazing process to behold. I've been involved in standards work of one kind or another, for close to a quarter of a century, and I've never seen anything happening on this scale and at this kind of a pace. And so I have a concern that we may not do as good of a job as we should of being sure that all these different pieces fit together in the right way, and we may end up causing some problems because of the pace of development that are going to have to get sorted out later on. So I think there are going to be some mistakes and maybe even some failures along the way, which I think will have some consequence. So I think that's one kind of risk. Another kind of risk is what happens if we don't do anything at all. I think there's a lot of evidence in the United States, and I'm not sure how much it applies in Europe, that the system we have now is very fragile. It's become much more common to have electrical power outages. I mean, it may come as a surprise to folks who are involved on the call, but I live about 25 miles from the White House, right in the heart of, near Washington, D.C., and the utility that provides my electricity in my home is one of the most unreliable in the United States. We have had a real history of power outage problems due to storms and other kinds of events in recent years. And there are real problems with the reliability of the grid as we now have it, even though people think of it as pretty dependable. And I think that as we put more strain on it, those things are going to increase. And I think that we're looking at significant capital costs in terms of meeting demand. We're sort of stretching the generation capacity that we have now. And there are huge financial consequences and possibly environmental consequences of just trying to build more and more of those things. So I think the cost of not doing anything is also quite large, probably larger than the cost of making some mistakes along the way as we move ahead. That's probably the best way I can characterize it.
Fantastic. Thank you, Stephen. That summed it up very well. Great note to finish on. We can't go on in the old way. Otherwise, all the lights are going to go out, basically. Stephen, thank you very much on behalf of our worldwide audience and all of us here sitting in London listening to you. We found that fantastically informative. I think that's moved us on. We've had a many thanks come through from one of our people online, so we'd like to echo that. We'd give you a round of applause and buy you a beer if you're actually here, but we'll just go and have the beer for you.
You can have a beer for me, and next time I'm in the UK, I'll be happy to have one with you in person.
Absolutely. We'll treat you.